The next topic is the celestial sphere. So we introduced it a little bit here. So what we have here is a piece of the celestial sphere. On campus we have this great planetarium, Moorhead Planetarium, where you can go into I should point out the difference between a planetarium and an observatory. A planetarium is a dome. You go into the dome and they project pictures of the stars or anything really these days with digital technology into the dome. An observatory is a place with an actual telescope that you're looking out into the sky, the real sky. Now, to simulate the celestial sphere, you can either just go out at night and look at the real sky, or you can go into a planetarium and they'll project all the stars, and you can do nifty things. You can move into the past, you can change time, you have all that control in a planetarium chamber. And Moorhead Planetarium, it's the largest planetarium in the southeast of the country. Famous, historically, all the Mercury, Gemini, and Apollo astronauts trained there. They learned celestial navigation there. And on 3 instances, what they learned at Moorhead Planetarium actually saved their lives out in space. So it has a nifty history as well. But we're not in the planetarium, so I can't fill our classroom with stars. You just have to use your imagination. I got a little chunk of the celestial sphere here. Imagine it filling the room. So let me ask you the question. We'll just do the basic question right now. How does this move over the course of the night? And to understand that, we have to orient the room. So if we're going to orient the room, which way is north? That way. Franklin Street's that way. That's how I remember. And so south is that way. Which way is east? Back there. And west is over here. So in general, the stars rise where? In the east and set in the west. So from our point of view, the celestial sphere rotates about us. The ancient Greeks thought that's what was actually going on. But in reality, what's going on, as we know today? Yeah, Earth is rotating underneath it. So if the celestial sphere is rotating from east to west, that means Earth is rotating from where to where? West to east. Okay. So we'll pick up with that next time. So if the stars are moving from east to west, I mean, we got 2 possibilities. The Earth is sitting here, and the whole universe is rotating around us. Sounds crazy, but that's what they believed for thousands of years. That's the ancient Greek model. Or the stars are out there and Earth is just spinning on its axis. And we all now know in the modern day that's the case. But back in ancient times, ancient Greek times, it was a reasonable idea to think that the Earth is stationary. I mean, if you're on a merry-go-round, you feel the rotation, right? You want to be thrown kind of to the outside. Or if you're on a track driving your car or some vehicle, you're kind of pushed to the outside. Do you feel Earth's rotation? No, you don't really feel it. But there is a force. It's called, you do have the same kind of feeling. You are being pushed slightly to the west, I think it is. It's called the Coriolis force, and we'll talk more about it in lesson 2. But if you crunch the numbers, the size of the Earth, and the rate at which it's spinning, the force that's inferred from that, it's small compared to the force of gravity. So gravity is our attraction to the center of the planet. All the mass is beneath our feet. Gravity is an attraction between masses. So we have this pretty sizable force pulling us down. So we don't really notice the small force pushing us to the side, the Coriolis force. So back then, it seemed a very natural idea that Earth is stationary. Also, we kind of like, historically, psychologically, we like to put ourselves at the center of the action, center of the universe. So we just thought back then Earth was the center of everything, and everything naturally would go around us. So that was the ancient Greek idea, and we'll explore that a lot more in lesson 2. But the idea was all the stars and everything in the universe then went around us once a day, with slight variations for different types of objects. But we now know, and we'll come to that conclusion as we go further on in the course, that it's the opposite. Earth is indeed spinning on its axis, and if the stars are going from east to west, that means Earth is rotating in which direction? West to east, the other direction. So we can do it a couple of different ways here. I have a globe that we can use for different things, and we'll use for different things. And I've already busted it. There we go. And so the globe, west to east, well, it's kind of hard to see, so let's not use the globe. I mean, for those in the back, you really can't see the details on the globe. So let's use an umbrella instead. You can think of it, we can use this for many things. We can think of this as part of a globe, like this is the northern hemisphere of the globe. You can just envision the rest of it down beneath, use your imagination. And so let's pick some area to be the United States. So here's the United States. And so we got a west coast and an east coast. And I'll just mark it with sticky notes that I brought and spilled water on, so hopefully they still work. Okay, so we'll let this be the west coast of the United States, so maybe that's LA. And there go my sticky notes. And where is it? This will be the east coast of the United States, so this is New York. So west to east motion, that means we're going from LA to New York, so this direction. So this is the direction that the Earth spins. Is that clockwise or counterclockwise? Counterclockwise. Is it clockwise or counterclockwise? Clockwise. So when we say the Earth spins counterclockwise, and that's how we normally refer to it, we're talking from as viewed from a particular direction. If we view it from down underneath the Earth, it appears clockwise. If we view it from over top of the Earth, and by over top I mean if you ran up to the North Pole and jumped out into space and then looked down, it'd be a counterclockwise rotation. It's important to define that because the solar system, all the planets are in a plane. And all the planets, for the most part, there are some exceptions, they all rotate in the same direction. They all orbit around the sun in the same direction. And so as viewed from the top of the solar system, over top of the north poles of all the planets, at least approximately, everything seems to be moving counterclockwise. Even the sun rotates on its axis counterclockwise. But from the bottom of the solar system, there's no top or bottom in space, but we can define one plane of the solar system. Everyone go to their north poles and jump off and look back down. It's a counterclockwise motion. So that's just something good to keep in mind. Let's see. Okay, so the Earth rotates counterclockwise as viewed from the top down. So, okay. So Earth is rotating counterclockwise. Maybe we'll use both the globe and the umbrella. The globe can be the Earth. And now we'll let the umbrella be not the Earth, but the celestial sphere. So I'll just extend, here's Earth. It has a rotation axis. And I'll just extend that axis with the shaft of the umbrella here. Now Earth is rotating, I'll get going the right way, west to east, so that's in this direction. So in the sky, as we said, not in the ancient Greek model, but modern day realization is the sky is just standing there. Again, we talked about the celestial sphere. We can envision all the stars as painted on a sphere that encompasses us. It's not reality, but since we can't see distance, it's equivalent. So let's keep our construct of the celestial sphere. Here's Earth rotating underneath it. Now, from the point of view of someone on Earth, as I said, we don't feel our rotation. So it's equivalent to say Earth is standing still and the sky is rotating in the other direction. Here, we're going around, yep, that's counterclockwise from the top. So we can equally think of us standing still and the sky rotating around us. Make sense? Okay. So my question to you, is there a point in the sky where the stars do not appear to move as viewed from Earth? Yes or no? Yes. In fact, there are how many points? 2 points, that's right. And so we call them not the North Pole and the South Pole, but the North Celestial Pole and the South Celestial Pole, to distinguish it from the North Pole, which is where Santa lives, and the South Pole down here. North and South Pole of the celestial sphere. And really, it has nothing to do with space. It's just an extension of our particular planet's rotation axis out intersecting this imaginary sphere that we believe all the stars are painted on. So let's write down those terms. Okay, celestial sphere. So we have the North Celestial Pole, and we have the South Celestial Pole, which is just an extension from through Earth's rotation axis through the South Pole out to the idea of the celestial sphere. Now, there's a star very close to the North Celestial Pole. What do we call it? Polaris, yeah. Sometimes it's called the North Star. Its technical name is Polaris. And so it's, again, along the pole of Earth's rotation axis, continue out in that direction, and we have a star. It's not exactly at the North Celestial Pole, but it's very close, and it's relatively bright. I mean, if you go faint enough, you'll find something close enough to either celestial pole. But it's relatively bright. Now, if you're looking in Chapel Hill, if you go out looking for the North Star, looking for Polaris, it's hard to see in Chapel Hill. It's bright compared to the vast majority of stars out there. It's kind of faint compared to what you can see with the human eye under city conditions. If you go outside of the city, particularly on a moonless night, you should have no problem seeing it. In fact, it's easy to find. This is kind of total tangent, not where we need to go, but one of the easiest things to find is, I said we're not going to learn constellations, but I can't help myself. One of the easiest things to find in the sky is the Big Dipper. So here's the Big Dipper. If you take these two stars on the Big Dipper and just continue off in that direction, you'll find a fainter star. And it's actually on the end of the handle of the Little Dipper. And the Little Dipper is sometimes hard to see because some of the stars in the Little Dipper are very faint. And if you're looking in the city, it won't look like the Little Dipper because you won't see them. But you might be able to see Polaris under city lights, and that's how you find it. If you're having a hard time finding it, another trick is to line yourself up on street grids. Streets are normally north-south, east-west, so if you get on a street like MLK or Columbia that's on a north-south orientation, look to the north, just follow the street and look up, and you should find it as well. Anyway, it was used going back through history to help navigate ships. You know, you're out at sea, which way's north? Well, you find that star, and that star's always there. It's not moving like the other stars. You latch on to any other star, it's moving in the sky. Not very good for navigation, but there's that one star that's always there, at least when the sun is down and the sky is dark enough to see it. So it has a unique place in history, but we'll see it's not always there. It moves, it's not always close to the North Celestial Pole. All right. Let's see here. Okay, here's a question. If we were standing on the North Pole of Earth, where would the North Celestial Pole be relative to us? To our left, to our right? Up, right? It's straight overhead. Because the North Celestial Pole is an extension of our rotation axis. If we're standing on the North Pole, imagine a little person standing here, they'd have to look directly overhead to see Polaris. So Polaris would be up there. So let's see, I got a figure here. Kind of shows that. Here's Earth. And here's its rotation axis extended out to meet what we're calling the celestial sphere. Again, envision all the stars painted on it. Here's our North Celestial Pole, South Celestial Pole. So you can envision standing there, you'd actually have to bend your head all the way over and look up to see the North Celestial Pole, to see Polaris. But we're not on the North Pole, we're here in North Carolina. Granted, North is in both names, but it's not the North Pole. We're partway down on the Northern Hemisphere. So is that North Celestial Pole still straight up? No. Remember, we oriented the room north, south, east, west. So go ahead and point to where the North Celestial Pole appears in our sky. That's right, it's partway up the Northern Hemisphere. The farther we go down to the equator, the closer it gets to the horizon. So let me bring up another image that might help to illustrate this. So here, same kind of figure, except it's tipped over. Here we have the Earth. Here we're standing, I guess, in North Africa or Southern Europe, but that's kind of, rotate the Earth a little bit. It's like you're standing in North Carolina. Pretty close anyway. And so here's the line going through the rotation axis of the Earth, North Pole, South Pole. You can see it well here. And where it intersects with the fictitious celestial sphere, which gives us our North and South celestial poles. Now, the point directly overhead in terms of terminology, we call that zenith. That's a term that we'll use. Zenith means directly overhead. Doesn't mean directly overhead the North Pole. It means directly overhead of wherever you are. But indeed, the North Celestial Pole is not up here at zenith like it would be at the North Pole, but down here in the northern sky. Here's north, south, east, and west, so it's in the northern sky, closer down to the horizon. If you keep moving down farther to the equator, then the Earth is tipped on its side, and so the North Celestial Pole will be on our horizon. So if we're near the North Pole, it's up there, and we start marching down towards the equator, it moves down and down and down until it's on our horizon, and all the stars will be going around it at that point. Now, this introduces some extra terminology here. And these are called, in particular groupings of stars, called circumpolar stars. These are stars that never set or never rise around the two poles. You can see a mark here. There's a circle on this diagram going around here. So if that's a star, it's going around, it gets high in the sky, comes down, gets close to setting, but doesn't quite set. And everything interior to it, closer to the North Celestial Pole, will be the same deal. It will move around the North Celestial Pole, but it's a small circle, and the pole's high enough up that it never sets. So there are some stars that never set. We call those circumpolar. And down in the southern sky, around the southern celestial pole, you have stars there that never rise. Anything within this cap, we can't see from the northern hemisphere. Those stars are always below the ground. It makes sense. We're in the northern hemisphere. We're not going to be able to see part of the southern sky because the Earth is in the way. So those are circumpolar stars. That make sense? Question?
So if you're on the equator, ideally you can see all the stars in the sky.
That's right. In fact, you just answered one of my upcoming questions. But yes, indeed, if you're on the equator, you can see all the stars in the sky, except, of course, when the sun comes up. The sun comes up, it scatters its light all throughout the sky, and you can't see the stars anymore. But wait 6 months, and then the other set of stars will pop up. Okay, a couple questions for you, one of which was just answered. But if we were at the North Pole, which stars would be circumpolar? Standing on the North Pole, all of them. Yeah, all of them. All of them would be circumpolar. Oh, I got a nifty slide. I'll come back to that. So yeah, there's the polar bear that I mentioned. And since all the stars are going around that point directly overhead, as you extrapolate that down to the horizon, they're going sideways along the horizon. All those stars never set, they never rise, they're always above you. You see half the stars in the sky and they're always up. Even when the sun's up, you just can't see them. And the other question, which was answered there, if you're standing at the equator, what fraction of the stars are circumpolar? And the answer is none. None. So here we are at the equator. And remember, if you're standing on the equator, let's see, north was that way. So the north celestial pole will be there, the south celestial pole will be there, and maybe this will help illustrate it. We'll stand on the equator. So here's the Earth, here's the equator. As I said, my screens don't let me touch anything. There's a reason. So if you're standing here on the equator, then the north celestial pole will be along the rotation axis in that direction, the south celestial pole will be in that direction. So here's your ground, your horizon will be there, and the stars will come up in the east and set in the west. Over there, they're coming up in the east, setting in the west. East, west, and same with the southern sky, coming up in the east, setting in the west, rotating around those two poles. So all the stars rise, all the stars set. So none of the stars are circumpolar if you're at the equator. Okay? Okay, let's go back to this figure that I skipped, because it's kind of cool. I said we're in the northern hemisphere, which we all agree on, and that means the north celestial pole is not straight overhead, but somewhere in the northern sky. So here's a picture. I'm not exactly sure which observatory this is. I always think it's Kitt Peak, which is near Tucson, and that light in the background is Tucson, but that telescope isn't one of the telescopes at Kitt Peak. Kitt Peak's, well, in Arizona, near Tucson. Anyway, it's some northern hemisphere observatory. It might be Mauna Kea in Hawaii. I'm not exactly sure. But anyway, this is a time-lapse photo. And so, it's actually quite dark. It seems bright. It seems like sunset or sunrise just because the camera shutter is open all night. Every little bit of light that comes in gets counted and accumulated over the course of the night. And so, the camera's sitting on the ground, so the telescope's not moving with respect to the camera, it's always sitting there. You can see the cars that came in and left over the course of the night, leaving the trails of their headlights in the exposure. The stars rotate around the north celestial pole, so you can see that motion there. You can see where the north celestial pole is. It's hard when you just go out. You see stars, you're not exactly sure which one is the north star. But in time-lapse photo, it's pretty easy. It draws a bullseye for you. So right there's the north celestial pole. This bright star is, guess what? Polaris, yeah. Now, Polaris is actually kind of hard to see, say from Chapel Hill. You go out, on a good night, you can maybe see it. Or if you get out of the city and the moon is down, you can see it pretty easily. But it's a relatively bright star compared to other stars. Most of these other stars you wouldn't be able to see with the naked eye. It's only because it's being captured on film, collecting extra photons that the eye can take in and store to see them. And another nifty thing you can do with this image, you can tell me approximately how long the exposure was, how long they left the camera open.
Anyone want to venture a guess? About 8 hours, yeah. Because a full circle would be 360 degrees, of course. Would be 24 hours. A full circle would be 24 hours. Of course, we can't. The image would be pure white. It's the daytime hours. So it's about a third of a circle, a little bit more than a third of a circle. So I'd guess like maybe 9 hours. So the sun went down. You had 9 hours of night this time of year, and then they finished the exposure before the sun came back up. All right. Any questions about that? Okay, I'll point you to the first exercise. Now, these exercises aren't graded. They're just things I'd like you to go out and try to do. So, go back to the course homepage. They're all written down in the math notes. So if we go down here to the bottom, exercise 1. Now, they're not graded, but, I can ask you about these on the exam. So I encourage you to go out and try it. This one's meant to convey a sense of what we just talked about, all these motions of the stars. You go out and take a quick look at the sky, you don't see the motions of the stars. Right now it's just an academic subject in your mind, most likely, unless you really stare down for long periods of time. So I encourage you to go out and make a sketch of the northern sky and a sketch of the southern sky from some locations, some fixed locations, and include some buildings for reference. Maybe you have the bell tower over in the south or something like that. And draw, you don't have to draw every star in the sky, but the bright ones, maybe you can identify a few constellations, and just draw them with respect to the buildings. Maybe you do this on Friday night before you go out to have fun. You quickly draw your sketch here and sketch in the north, and then come back a few hours later, giving the sky time to rotate. And so, yeah, your second set of drawings might be a little blurry, depending on what you're doing, but do it again. And what's your expectation? In the southern sky, what do you expect the pattern of stars to do? Yeah, they're going to move, that's right, clockwise, in a broad, sweeping pattern across the southern sky, because they're rotating around the south celestial pole, which is beneath the ground. So this is the outer part of the circle, a big, giant circle across the sky. But in the northern sky, what do you expect to see? Yep, it's going to be rotating the other way, and it's going to be a tight circle around the north celestial pole. So you should notice a difference in the motion of the pattern of the stars if you do this. So I encourage you to try it. It works best on a moonless night. It works best if you have opportunity to get away from the bright lights of Chapel Hill, but that's not a requirement. But if it's moonless night, maybe that's in clear night, of course. Clouds will ruin this. You might want to give it a try. Questions about that? Okay.
I had a really nice big umbrella, and I went looking for it and couldn't find it. So I went to my postdoc's desk to steal his umbrella. He's away. I was just going to steal it. And shortly before class, I opened it up and was shocked. I was horrified at what I saw on this umbrella. And I just couldn't imagine if I had brought it to class and opened it up to see it has a big Duke emblem right here. And I probably would have been mobbed by you all. And so I got rid of his umbrella, and I'll fire him as soon as he gets back from vacation.